And here we are. Welcome to this chapter on wave propagation and time step selection in the context of flexible particle models. We start with the underlying theory that allows us to understand the transient deformation behavior of a beam, which is the well-known Euler-Bernoulli beam theory. This theory is a continuum theory, meaning that we assume that we have a homogeneous beam with material properties that can be defined at each point along it. Also, you will see that there is no external force acting on this beam. Even gravity is switched off. Thus, we look at the so-called natural frequency of a beam. A beam under such conditions is illustrated here in the undeformed state, indicated by the straight and slightly transparent blue line, as well as the deformed state, see the dark blue line. Important is that the beam is considered to be fixed at the left-hand side to a rigid wall. Its deflection and slope is zero at this point. Of course, we have to keep in mind that in our DEM model, this beam is approximated by a 1D flexible particle model, meaning by multiple point particles and bonds between them. One can now write down a differential momentum balance in the z direction, which is the lateral direction that is indicated here on the left. Note that the local beam deflection is denoted as W. Thus, the shape of the beam in the deformed state follows a function W of x and time. If we now make some assumptions such that the deformations W are small and that there is no shear deformation, we arrive at the Euler-Bernoulli partial differential equation. As you can see, we have a second time derivative. As you might anticipate, this term reflects the local acceleration of the beam and a fourth order derivative in the space coordinate x. This latter term is difficult to interpret on the first view, but as you will see once you dive deeper into literature, it simply quantifies the restoring force due to the bending of the beam. Thus, in essence, this equation balances the local inertia of the beam with the local restoring force due to the beam's internal stress as a result of its deformation. The variables in front of the inertia term are the mean beam density, ρm. Please do not confuse it with the particle density in our bonded particle model. We will come back to this later. And the cross-sectional area of the beam AQ. The terms in front of the second term are the well-known Young's modulus, as well as the area moment of inertia we have seen already at the beginning. You might fear this partial differential equation, and it looks quite complex to solve. Fortunately, deformation and vibration behavior described by it have been analyzed by generations of engineers, and the publication of Guo et al. Summarizes the corresponding results in an excellent way. And indeed, the solution for the eigenfrequency f is relatively simple. Please note that the Euler-Bernoulli differential equation gives multiple eigenfrequencies, but for the sake of compactness, we refer with f only to the so-called first mode, i.e. the lowest eigenfrequency, and lambda is the smallest dimensionless parameter, which is called the first eigenvalue. We now need to connect this solution with our bonded particle model. Also, this is quite easy. First, we replace the product of the mean beam density with the cross-sectional area with mu-LD, which we call the mass per unit length or the line density. The latter is perhaps a bit misleading, that is why I do not like it. Also, we note that the eigenvalue for the beam deformation sketched here on this slide has a value of 1.875. We note in passing that these eigenvalues depend on the boundary conditions, i.e. how the beam is suspended, and that there are multiple eigenvalues, but we here look only at the lowest one as already mentioned. What follows next are results that follow from straightforward algebra. First, this is the period of the pending vibration, which is simply the inverse of the eigenfrequency. As you can see, it is proportional to the square of the length of the beam, and hence our flexible 1D particle, as well as the square root of the ratio of the mass per unit length and the stiffness. This already reminds us of the Rayleigh time. Thus we are definitely going into the right direction with our analysis. On the right hand side we now see the expression for the bending wave speed. Again, you see the mass per unit length and the stiffness matter. We can now make the final decisive step in our analysis. We consider the time needed for the bending wave to travel exactly one bond length. This length is our primary particle diameter dp. If we do this, we arrive at this simple expression. We now have to recall the structure of our 1D BPM to write down the equation for the mass per unit length. As you see, we simply consider one bond which is populated by two half spheres, so one full sphere, and the distance is of course 1 dp. Also, we recall the expression for the area moment of inertia. To arrive finally at this important analytical result. Most important, rho p is here the particle density and must not be confused with the mean beam density rho m. We now just evaluate the numerical parameters and see that we get a relation that is in full analogy with the Rayleigh time we have discussed in the context of our contact force models. Finally, we may observe that L over dp is nothing else as the number of bonds in our 1D BPM. Excellent! This allows us to calculate the time scale of the bending motion that we have to resolve with our integration scheme. The question is now, how small are the other time scales connected with the dynamic behavior of our 1D BPM? To answer this question, we have to analyze two more vibration modes: the axial or stretching mode of vibrations and the twisting vibration. We will see later that twisting is not important since these vibrations are of relatively low frequency. Thus, it only remains to analyze the axial vibrations, which we do next. Again, we ask the question, what is the time needed for a, in this case, axial wave to travel one bond length? This requires us to know the axial wave speed. This is fortunately very easy to get. It is given by this relation here. Putting everything together and using the fundamental equation for the time delta t axis, we get this nice analytical expression below. If we now evaluate the leading numerical term, we see that the time step restriction from the axial vibration is considerably more critical than that from the bending motion. Thus, delta t axis dictates the time step in a bonded particle model simulation and is even more restrictive than the restriction due to the Rayleigh time. With this, we can close this chapter now and move on to our summary session.